Great. Graham, working with you on optimization and the digital twin idea. Probably the most exciting clip of the lot. So here's the skinny on this. We're going to look at this optimization panel here. We can get that to change. And this is where we've got really a mixed integer linear program. So I'll go through the detail on this carefully. Some changes in these numbers are going to be necessary to sort of push this through. So essentially what, sort of the big picture of what this optimization tool is doing is it's making, basically a whole variety of changes in concert. So for example, changes to the cadence, changes to the number of anesthesiologists, surgeons, PAs, CRNAs, and so forth, with the aim of maximizing an objective function. This is a heuristic optimization, so you're not getting an exact optimization. And one of the reasons for that is this is a combinatorial optimization, and so the sort of the computational complexity of solving it exactly, the challenge of solving it exactly blows up as the number of combinations increases, and that's definitely the case here. Because you're looking at changing simultaneously, tracks A and B, anesthesiologists in track A and B, and the CRNAs, and the EVA staff, and the registrar, and the cadence, and so forth. So let's just have a look at the parameters and sort of get a sense of, how many possible changes are entailed here. So this is the inter-arrival time of track A. These are patient inter-arrival times. And I've chosen to do this on a discrete basis. So looking at values between 90 and 130 in steps of 10. So like literally 90, 100, 110 on up to 130. Same for B. Saying that the registration times are fixed at 15 minutes with a 2-minute standard deviation, and the sedation time similarly fixed. Some of the surgical times for both A and B. But here it goes. For the anesthesiologists who are entertaining between 1 and 3, stepping one at a time. So 1, 2, 3. For B also, 1, 2, 3. For the surgeons, same, A and B. And then for the ORs, for track A, we're saying we're going from 0 to 5, one step at a time. So from B, 0 to 5, one step at a time. Reason I'm going up to 5 and not 6 is so that at least one remains in the pool or, in the other track, because we do need to cover both tracks. Both tracks need access to at least one OR. And then the EVS pool folks going up from 1 to 3, one step at a time. Not really changing much about the registrars, allowing one reduction there. For the pooling of the ORs, anywhere from 0 to 6. And then CRNAs anywhere up to 12. PAs up to 6. And then the patients anywhere from 5 to 10 being scheduled, both tracks, stepping in one at a time. So you're probably thinking, okay, that looks like a wild range of parameters, and that's not respecting things like dedicated anesthesiologists and surgeons to each track, and that's fair. So we are going to have some constraints that are going to apply prior to a run beginning. And so here they are. This first one says that if I take the total number of anesthesiologists dedicated to A and B, and I subtract the number of CRNAs, 2 times the number of CRNAs, that number must be greater than 0. What that basically requires is that the number of dedicated anesthesiologists in track A and B exceed the number of CRNAs by 2 times the number of CRNAs. And then same sort of idea for the surgeons. We cannot have the number of PAs exceed the number of surgeons, so that enforces that constraint. Also forcing you to put one surgeon into track A dedicated, same for B. One anesthesiologist has to be dedicated to track A and B. And then the total number of ORs dedicated to track A and B and in the pool less than or equal to 6. And Okay, so those are enforcing those requirements on the staffing, and also on the ORs. And then we're going to require certain conditions. They call these requirements that apply after a simulation run has been done to see if it's feasible. And all of these are those burnout utilization red lines. So you can see for the registrar, anesthesiologist, those averages. Getting back to our simulation, basically, let's see, here's the main canvas. So it's referring to these quantities here. So the util NSA measures the average utilization of anesthesiologists that are dedicated. In fact, the util PA would be the average utilization of PAs in that PA pool. All right, so hopefully we're referencing, relevant numbers there. And this language here, root, just appeals exactly to those quantities that I've just shown you on the canvas. So registrars, anesthesiologists in A, B, CRNAs, surgeons in A, B, the PAs and the EVAs, everybody's got that default 50% burnout red line. You'd have to come back and fix these. So definitely going to make changes there. I think these are pretty much fixed. I don't expect you to have to change anything here, but these 0.5s definitely gonna need some attention from you. All right, so now this objective function, how does that go? So look, so this one is the revenue. What we're doing there is we're operating 200 days a year. Go back and just have a look at that with you so that you convince yourself that it looks fair. So I want to go back to main. And I'm using these two terms here. So this revenue function, let's see what's in that quantity. So it's 200 days, you're getting 22K of surgery, and then it's the number of surgeries that you complete. And that's these quantities here, okay? And then for this penalty term, patient penalty, let me just expand this so you can see what's going on. You're for each day, paying $50 per flow time minute, dividing this by 1,000 because all of these numbers are in thousands. And then instead of just using the surgeries, I'm multiplying by the number of patients that you actually schedule. You may not finish all of them. So it's the average flow time by the number of patients because that, if they've been scheduled, either they make it through the process, they get a flow time, or they sort of get held up and they get bumped to the next day. Either way, you're going to pay for every patient you schedule, the average flow time, multiply that by 50, and then by the 200 days. Okay, so quite expensive, and you want to watch how many patients you schedule here with a known patient. You want to bring that down so that it's basically just what you can complete. You don't want folks being scheduled and getting bumped to the next day. All right, so let's go back here. So I'm hoping that those two terms will be fine for you, root.revenue and root.patient penalty. They come directly out of that canvas. And then the other things that we need to deduct from this sort of modified, this tentative profit number we're busy developing is are the salaries across the board, and then also amortized cost of the ORs and any maintenance OpEx type costs. All right, so here are the salaries. So the first one we've got here, see if I can expand this all the way across here. This is for the ORs. So you've got the number of ORs in A and B, and then in the pool, kept at 6, of course, by that requirement further down. And then there's 220 in amortized cost, which is basically your CapEx and spread over 10 years. And then also 200 for maintenance and utilities and whatnot. So total comes out at 420. If you want to revise these numbers, do so, but with justification. And then on the surgeons, we're saying they get 650. and um, and then there's 200 for the PAs. So these are all deductions, right? And then slide this across here. 393 for the anesthesiologists, 60 for the registrars, 60 for the EVS pool, 200 for the CRNAs. All right, so that is in revenue minus the patient penalty, minus the salaries, minus um the OR costs. Okay, so what else to know about this? It's using a genetic algorithm, and you can research this. Basically, it's using genetic operators supposedly to come up with proposed changes to all of these quantities that are available for change, like the number of anesthesiologists, the cadence, and so forth. These are all discrete changes. And hopefully it's going to converge to something that is better than what we had current workflow, but progressively it works to try and optimize this function because it's a heuristic optimization. It's actually a meta-heuristic genetic optimization. There's no guarantee that it finds even a good solution. Could get stuck in some sort of local optimum. And we're going to see what happens if we repeatedly run this. We may get different solutions, and those solutions may actually look radically different from each other, raising questions about the utility of this tool as a digital twin, just sort of like out of the box. Using it as a cobot where it's a decision aid, a decision assistant, that would be a different situation altogether. Okay, so what else do we want to know here? So there's randomness. Every time we run it, we are going to get randomness, and that's because of this random seed set to give us unique simulation runs. And then we're getting 10 replications. Every time there's a set of parameters, whatever they may be, it runs those simulations 10 times and then uses the average of those results. So that's helpful. It's taking care of a lot of the lift. So let's go ahead and run this thing. I want to just get to the optimization. So when you change anything here, you do need to create default UI. Okay. And then we're going to run it. We don't run the simulation, we run the optimization. So you can see I have HipHopBERT2 optimization. Let's see if it runs here. Okay, so these are the values that it's gonna, in the whatever the current iteration, it's gonna run. I think it's up to 500 is allowed, with the free version that we have. And using this genetic algorithm. There is incidentally an alternative optimization engine called OptQuest, but the number of variables that we have requiring optimization here exceeds the limit of the free OptQuest demo. So we're limited to just the genetic algorithm, the built-in one. There are ways of, working on more sophisticated optimization strategies here using, Java code. But we're just going to use the out-of-the-box genetic optimization here. So you can see everything that is changeable shown in blue. The ones that are fixed values are shown here in black. And then it's going to score each set of parameters. In other words, each proposed scenario, score it, show if it's feasible or not. And then it's going to keep track of the best one here. So let's go. All right, so it's running here, and you can see that the current ones are all infeasible. It hasn't found a feasible solution yet. And the red just shows the best infeasible one. Hopefully it's eventually going to find something that we can use. That it's not the case. Okay, so let's try that again. And one of the things that I think is happening here is those red lines are really restrictive. So it's just simply not able to find any solution that meets those 50% limits, red lines. So you're going to come and revise those, and presumably you're going to find it's giving you a solution. So let's just try this again. Notice how it doesn't step up, it just sort of flatlines here. Try it one more time. Okay, so it did find an optimal, a feasible solution here. And when you get the feasible solution, it shows in blue. You can see progressively it increases because we are maximizing that profit function. All right, so a little disturbing, right? We ran this thing 3 times, 2 infeasible solutions. Now we've got one that is feasible. Let's go ahead and just pick through this solution just to see what it suggests here. So it's the cadence is the original cadence of releasing patients or scheduling patients every 90 minutes, putting three anesthesiologists in each track, 2 surgeons in each track. It's dedicating an OR to B, but not to A. And it's got another 4 ORs in the pool. So B has access to a total of 5 ORs, 1 dedicated, 4 in the pool. A has access to only 4 ORs. There are no CRNAs, no PAs. It's scheduling 6 patients in each track. And what else? Yeah, 3 EVS people. And how many registrars? Just 1 down here. Okay. So that's the bottom line. So let's just think about it. So there are no PAs and CRNAs, so there's no question about surgeons or anesthesiologists, about the CRNAs or PAs sort of being in an inappropriate ratio to the anesthesiologists and surgeons. We are dedicating, appropriate talent to each track. There is at least 1 anesthesiologist for both tracks and 1 surgeon for each track. So the staffing considerations are all fine. Now, let's go ahead so this is a $30 million profit. You can verify those utilization red lines by hitting copy best, and you have to say allow here. I'll close this, go back into our simulation main where we put these values in, and then we say paste from clipboard, and it's gone ahead and substituted all the optimization suggestions in here. And now I can go ahead and run this one. So just verify what's going on. I see the log is going to ding me out again here. It's got a little cross on that. So let's just see, maybe it's going to go through. Probably, yeah, it's going to. So just going to go ahead and right click to delete the log and run this now. Okay, so I mistakenly ran the optimization. I want to run the simulation again with those changes that I've made. Okay. And I run this to completion. So I'm getting the 6 surgeries. And here are my utilizations. The registrar is at 422 because we dropped from 2 to 1, right? So that bounced it up, but we are saving a salary there. EVS folks are at 13.8. Don't know why we've got 3. That seems a little rich. Okay. Don't know why we need 3 there. In any case, anesthesiologists are in the 35 to 40% utilization range, 38 to 42. These are a lot of numbers, right? So that, the 50% burnout default, just not good. You're going to have to fix that. But I think it just illustrates that, in fact, this proposed scenario does meet the red line. So I just ran it again, and you can see all my anesthesiologist numbers and surgeon numbers are in the 30% range. Again, getting in the 30s, and we'll try one more time. So I'm getting the six surgeries there. And I'm better than 30 million here, right? 135. So this optimization tool, certainly very interesting, right? It's doing an enormous amount of lift, changing all these parameters. So I think that's very positive. What wasn't so positive was it was unable to find even a feasible solution on those first two go rounds. And so if you were just sort of like using this out of the box and an automatic digital twin setting, not sure that it's your friend, but we did find a solution here that works. And so very interested to see what you're going to do once you fix the red lines and maybe make adjustments to some of the times, some of the salaries and so forth to mimic conditions that are maybe a little bit more realistic. Hope you enjoy this case. A lot of interesting ideas here, and this sort of extends the coffee case because now we have a network, right? We have sort of a linear tandem process with four stages as opposed to just the one stage in the previous case. Enjoy.